here, maybe we'll just advance it to 12:30. And so we have also arranged for dinner here in the evening, but so we are not very sure how many people will turn up for the dinner, because some people might go for shopping and then they might go to hotel. So I'll probably just pass a paper and just write your name if you come back for dinner. And I mean, even if you don't write your name and you end up here, it's okay. But we just need a rough count on the dinner. Yeah. So I think Manju has also sent a Google form, but if you just write it on the paper, it's okay. You don't have to. Yeah.
Okay, so thank you very much. We are here at the second session of the day. So there was a change. So we will have this morning Chandan and Srikant, and this afternoon Anupam and Kabir. So now we have Chandan that will talk about active matter.
Okay, thanks a lot. You can hear me, right? Mic is working. Okay, so I'd like to tell you about some work that we have been doing over the last 5 years or so on dense active matter. Some of you may have heard some of the things that I'm going to talk about today, because I've given talks on this before. So I hope there will be something new in what I'm going to say today. So this work was done mostly by these three people who were postdocs when this work was done. Deshpreet was a postdoc at Brandeis. Rituparna was a postdoc here, and Shumon is currently doing this work. And then there are several colleagues who are also involved in the development of this field. So here's the outline. It's the usual thing. I'll give a very quick introduction to active systems and also glossy dynamics and jamming, because we'll be talking mostly about this phenomena. Some thing about why we're interested in this kind of things. And then we'll talk about the model that we look at and some results. Hopefully, we'll have time for some concluding remarks. We'll see. So again, this is something that I don't have to go through. I mean, all of you are familiar with active systems. These are systems consisting of objects that can move by themselves, so to speak. They can convert energy into systematic motion. Many of these are actually from systems of living objects, but there are also now many experiments on synthetic active matter. We have already heard some talks about active matter in this meeting, but the things that I'll be talking about will be a little different in the sense that we'll be looking at dense active matter, and the phenomena that we'll be trying to understand deal with these things, glossy behavior and jamming, that show up only in the high density limit. And also we'll be talking about highly active systems, in the sense that, as we'll see, there will be something called a persistence time, and we'll be looking at the limit in which the persistence time is very long, and in that limit the effects of activity becomes most pronounced. So I'll be just a couple of slides just to tell you about the basic sort of phenomenology that we'll be interested in. Again, everybody is familiar with glass formation and glassy liquids. The problem has been around for ages. And what we are interested in is basically you start with a liquid, cool it rapidly so that it doesn't go into the crystal, but then it goes into a supercooled liquid, and if you cool it even further, then it goes into some kind of an amorphous solid state, which we'll call a glass. And in this talk today, I will be interested mostly in the supercooled liquid regime, where the dynamics becomes very important. And the interesting questions about this supercooled liquid mostly deal with the dynamics in this regime. And just one slide on that. Dynamics becomes very slow as one approaches this glass transition. And as you can see, the viscosity increases by like 13 orders of magnitude over a temperature range which is like 50 degrees or something like that. And I just want to make a distinction between sort of two classes of glass formers. These are all experimental data. This branch, where log of viscosity as a plot over 1 over t is a straight line indicating arrhenius behavior. This kind of systems are called strong, and where there is a very strong curvature of this plot, those kind of systems are called fragile. And we'll be interested mostly in the properties of fragile liquids, and many of the sort of model liquids that people consider in studies of glass transition belong in this category. Again, just one slide on jamming. We'll be also talking about jamming in active matter. So here actually what one is talking about is a system where thermal fluctuations are not important. So basically, we put the temperature to be equal to 0, and there the relevant parameter is the density or the packing fraction. And as one increases the density by squeezing the system, then it goes from a sort of flowing state to a state where the particles lose the ability to move around. And this transformation going from this where the particles can move around to where they're jammed is the jamming transition. And again, there are many studies of this and combining it with glassy behavior and so on and so forth. We'll not go into that, but the reason that we are interested in here is that how does this property, this behavior, the properties near the jamming transition, how do those things change as one introduces activity in the system? And we'll be particularly interested in behavior near the jamming transition, where there are some power loss, marginality, etc., that people have seen in conventional systems that exhibit jamming. So this is pretty much the introduction. What we want to tell you a little bit about, again, I'll go through this very slowly, very quickly, because there are many things to talk about. The reason that we are interested in glassy behavior and jamming in active systems is that, again, in the usual reason that there are many experimental systems for which one is beginning to see this kind of phenomena. And I have just listed here a few such examples. Many of them come from biology. And also now, with this artificial active matter, people are also doing lab experiments where you see this phenomena of glassy dynamics as well as jamming. Just 2 or 3 slides on typical experiments. This was one of the first paper that sort of made this analogy of cytoplasm that you see in cells with glassy liquids. And there they did experiment where they put a tracer inside a cell and looked at basically the movement of this tracer. And when the cell is in the active state, there is metabolic activity. This shows, the mean square displacement shows sort of typical fluid-like behavior that shows that would be appropriate for a liquid. It eventually, of course, saturates at long times because they weren't just looking at a small region in which the tracer is confined. But you see this linear behavior near the origin, indicating that when there is metabolic activity, the cytoplasm is behaving like a viscous liquid. But then one can add some chemical to it, and which basically turns off this metabolic activity, and then one finds that the tracer doesn't move at all. When it is plus DNP, basically in this situation, there is no metabolic activity in the cell, and one sees basically localization of the tracer. So one is basically going from dense liquid kind of behavior to a behavior when that dense liquid has become something like a glass, but the tracer particle is not moving anymore. There are now many such experiments on this. As far as artificial active matter is concerned, there have been experiments on these genus colloids, which sort of mimic the behavior of active particles. And there again, there have been studies which show the occurrence of glass transition in these systems. Again, I'll not go into details, but there are many things that people have observed in this artificial system of active matter. When one talks about jamming, again, there are lots of studies, but the one that I just mentioned very, very briefly is the one that has come out very recently, where one is looking at tumors, and the cells inside a tumor, some of them can be stuck, basically, jammed, or there are other situations where the cells can be motile, they can move around. And this unjamming actually is very strongly correlated with the probability that these cancer cells will move to some other parts of the body and induce cancer in those places. This is called metastasis. So now they have a handle on how to sort of predict the probability of metastasis, which is based on this kind of unjamming behavior, which seems to work better or as compared to the standard methods that exist these days. So these are important sort of phenomena that one is talking about. And so to sort of understand what is going on, we'll be dealing with some very simple model systems. Of course, I mean, eventually one is interested in these biological systems, but these are too complicated, so one basically deals with simple models, which are actually, in some sense, more applicable to the experiments on this artificial active matter, like genus colloids and things like that. But the basic phenomenology seems to be similar. So here, this is a cartoon of the kind of systems that we'll be looking at. 2 colors basically means that we are dealing with 2 different kinds of particles. Why do we do that? Because we want the system to exhibit supercooled liquid and glassy and glassy behavior. If we had just only one component and simple interactions, then such systems typically crystallize as you increase the density or lower the temperature. So to prevent crystallization, one basically looks at this kind of binary or even more complicated mixtures. That's what we are going to do. And we'll be looking at models that have been studied quite extensively in the context of sort of passive glass transition in the past. We'll be then introducing activity in a very simple way, and then we'll try to see how this activity affects the behavior near the glass transition. So there are some characteristics of activity in simple models. We'll be characterizing activity in terms of two parameters. One is the typical strength of the active force, and the other is called the persistence time. This active force here indicated by these arrows, that it itself changes direction. And this persistence time is the time scale associated with the change of direction of this active force. So these are the two parameters, in addition to the usual parameters that one specifies, like density, temperature, etc., composition, etc. Those are taken from studies of passive glass transition. And what we try to do is introduce activity and then try to see how that behavior changes. So this is the model. The model is known as Cobb-Anderson model. These are the people who sort of introduced this model in the context of passive glass transition in two-dimensional systems. We are looking at two-dimensional system here also. And it consists of two kinds of Lennard-Jones particles. Two kinds basically means that the Lennard-Jones parameters are different depending on whether you're looking at AA, BB, or AB. And the way the values of these parameters are also specified in this Cobb-Anderson model. And those are chosen in such a way that this system exhibits a supercooled liquid regime as you go to lower temperatures or higher densities without crystallizing. I mean, it would, in some sense, phase separate and crystallize, but that kinetically that process is very slow. So this is this potential, and then we look at high density. At this density, this original system, the passive system, actually would become a glass at low temperatures. Actually, here in this simulation, we'll actually put temperature equal to 0. So basically, the activity plays the role of, in some sense, trying to make the particles mobile and things like that. Yes?
So this potential is preventing from crystallization, or do you have different sizes also?
So this potential Lennard-Jones parameter will have a length parameter and a magnitude parameter. These are chosen in such a way that when you mix, again, this ratio also is important. When you choose things in this way, then people have found empirically that it remains in the supercooled liquid state as you cool it to lower and lower temperatures. So this is basically the equations that we deal with. I mean, all of you are familiar with these equations. It's an Langevin equation. This is gamma is the friction coefficient, and then there is the interaction term. This Lennard-Jones interaction, and whether it's A and B, etc., will determine this pair forces. So this is the passive model. And then in addition to that, we introduce this active term, which has a magnitude f, and in two dimensions, it is direction unit vector. Unit vector is specified by some angle theta, and we assume that this theta has a very simple dynamics, rotational diffusion. So there is a rotational diffusion parameter which defines the persistence time of the system. Okay, so everybody is clear on the model.
The blue-red also interact?
Yeah, everybody interacts.
So there are three types of Lennard-Jones.
Three types of Lennard-Jones potential. And those parameters are chosen to sort of prevent phase separation and crystallization. Okay, so now you see, in addition to we have fixed the density. Temperature has been set equal to 0. So there are these two additional parameters. One is this strength of the force. The other is the persistence time. And we have looked at the behavior of this model through basically simulations in this two-dimensional plane. And this work has been going on for a while. So I mean, I'll just flash the kind of phase diagram that we see. One is this tau p, one axis, and the other axis is the strength of the random force, persistent force. And one finds, as expected, that there will be, in some sense, two regimes in this phase diagram. One is the liquid regime, the other is the glass or dynamically arrested phase of the system. If you put F equal to 0, it's a thermal system, and then it's high density. It will be in the dynamically arrested phase. But as you increase F, then one finds an activity-induced fluidization of this dynamically arrested state at some value of F. And then, that value itself depends on the persistence time. So this initial part of the phase diagram is fairly well understood. In a very simple sense, one can sort of map the problem to a thermal problem in which the activity produces something that looks like an effective temperature, which depends on both these parameters, F and tau p. One can do more sophisticated theory, which is something that we have done. So there's something called random first order transition theory for loss transition. We can sort of extend that to include activity, and one finds basically how this melting of the glass, the value of F at which that occurs, how it depends on tau p. And the line that I have drawn here up to this point is basically a prediction of that. So this part I will not talk about today. This is something which is sort of fairly simple, and
So
yeah.
to be sure, so what you mean is that for low tau p, you have essentially a transition that you can understand.
It's similar to what it's similar to what happens in passive systems. Yeah.
For
Large tau p, then there will be. So that's the main topic of my talk today. That large tau p, the effect of activity becomes much more pronounced, and one begins to see different phenomena. Yeah. So, and now we look at this part, but the tau p has, so I mean, all these units are basically the standard Lennard-Jones units. So, so this tau p, when it becomes like that, then between the liquid and the dynamically arrested phase, one begins to see what is known as an intermittent phase. So I'll just flash a couple of transparencies on that. Not transparencies. I mean, I keep on saying transparencies because old time. And there are things like, things that look like turbulence and yielding, et cetera, in this regime, which is interesting. We have looked at it in great detail, but I'll not have time to go into too many details of that today. Today, I'll be looking at this limit, where the tau p has been set to infinity, where the random forces, they don't change their orientation at all. Once they're set, then it remains like that. So just to, again, this says basically what I told you, for small persistence time, one has a reasonable theory which sort of explains what one sees in simulations. For this part, when the persistence time is not so small, one sees this intermittent behavior, and this is important, so it will come up later on also. So I'd like to explain what one means by this intermittent behavior. What one is doing here is that in the steady state, one is plotting the total kinetic energy per particle as a function of time. And if the system is in a liquid state where the particles are moving around, then this kinetic energy will show the usual fluctuations that we are familiar with. But then, as one is making this F smaller, F in this regime, then one sees this behavior that one sees liquid-like behavior for a time, and then it looks like as if nothing is happening, its system gets jammed, and then again, it goes to the liquid-like state, et cetera, et cetera. So this transitions back and forth between two sort of states. In one state, the system is stuck, more or less. There is some fluctuation there also. And in one case, the fluctuations are liquid-like. This is what we'll call this is called this behavior, the intermittent behavior. And eventually, as you continue to make this F smaller, then of course at small enough F, it goes into the state where everything is frozen and the kinetic energy is 0 at all times.
And so this is not a final size effect. If you increase the size of the system, it remains persistent. It's intermittent.
Yes, as far as I know, I mean, we cannot do sort of very large systems, but over the range that we have looked at, and it's not just me. I mean, the next slide also, there are several other people who have done, in some sense, bigger simulations and so on. This is Ludovic Bartiers and his collaborators, and they also see that, and it has been seen in experiments, not on Lennard-Jones particles, but on granular systems, which has been done by Rajesh and others in Bangalore. So this is already a sort of new behavior, that when the persistence time has become somewhat large, then one has this regime where the system sort of goes back and forth between, I'm sorry, was there any question? jam state, and then jam state yields, and then one goes to some flowing state, and it goes back and forth between. We have looked at the statistics of intervals of this, as well as the width of these things, etc., again, available in that Nature Comp paper, and I will not go into further details here. What I wanted to talk about today, and this is ongoing work, and this is work done essentially by Shuan, who is a new postdoc, not new anymore, but the postdoc who is in ICTS. And here we are interested in the behavior in the infinite persistence time limit. So I just want to again emphasize what this limit corresponds to. It basically says that you assign these forces to individual particles, but once you have assigned those forces, these forces do not change further as a function of time. And this initially assignment is done randomly. So we choose the particles and say that this particle has this force in this direction, etc., etc. Once you have done that, that assignment is permanent. That doesn't change as a function of time later on as the system evolves in time. And this limit also has received some attention earlier. What we see here is some kind of a jamming transition. Now we see that the system, I mean, I want to make sure what I mean by this jam state. Here, there is no thermal noise. It's a thermal system to begin with. Time dependence could come from changes in the directions of the active force, but that also is not there in this limit. Once the directions have been chosen, those directions do not change as a function of time. So in principle, the system can be in a state where all the forces balance, this active force as well as the interparticle forces, and that's basically a sink of the dynamics. Once the system goes into that, it will not change as a function of time. And that state, with force balance state, is what I'll call a jam state in the system. And this transition again is seen in the kinetic energy. I mean, you know, now we are on this line. For large values of F, you see these fluctuations, liquid-like fluctuations, and then as F becomes smaller, then all these things die out. System goes into this force balance state and remains in that state forever. And this was also noted by Liao and Xu, and our study is basically confirmation of that. So now what I'm going to do is, the remaining 20 minutes or so, is to look at this limit. Look at the properties of the liquid state as well as some properties of the jam state, and see how those properties differ from what you have in a standard system without activity. Okay? So just a few words. I mean, this limit is sounds kind of strange. I mean, you know, it is very difficult to actually have an experimental system where the force doesn't change as a function of time. People tell me that now there are experiments on micro robots where they can do more or less anything that they want with the active force, and there is some possibility that one might see realization of that. Yes.
No, exactly. Even in bacterial systems, although of course there's a fluid involved there are mutants that don't tumble.
Don't tumble,
so
okay.
It's not as outlandish as you might think.
Okay. So once the initial orientation is chosen, it remains in that orientation, and the force is...
Interactions might make them change, but they don't have intrinsic...
Tumbling, yeah. There's one system that I know, which is a much simpler version of this, where this happens actually. This is a system of two kinds of particles, one positive charge, one negative charge, and then you put that in an electric field. So the positive charge forces will experience the force in one direction, negative charge forces will experience in the opposite direction, and these directions will not change because the charge is an intrinsic property of the particles. But this is just a generalization of that, where this force, instead of being in plus x and minus x, this force can now point in any direction in space, which you initially specify.
Since there's no noise, it should always go into the jam state. So why is there a transition?
Yeah, that's a question that we'd like to address in more detail as we come along. So the question is, you know, how long the system takes to get to the jam state, and how that depends on system size and so on. Yeah, those states are there, but again, you know, it's not rigorous. That now we have this random forces. So the jam states are actually, this is something what I was going to tell you here, is the local minima of this Hamiltonian. Right, this is the clear to everybody. This is the interaction Hamiltonian, and this is the Hamiltonian, so to speak, that comes from the external forces. And these Fi's are chosen in random directions. So the question is, you know, what are the properties of the minima of this function? And how many minima are there? I mean, you know, as you change F, then it is possible that the landscape changes and there's something is happening as a function of the magnitude of f. Yes.
How do you actually distinguish between this dynamically arrested state and the jam state in this topic?
Okay, so yeah, that's a good question. I mean, the jam state is one. It's a absorbing state, where the particles are in certain positions, and they remain in that position forever. Whereas the jammed, dynamically arrested state still has fluctuations. So you take a glass also, the particles on the average are more or less in fixed positions, but there are thermal fluctuations about that. In this case, it's a thermal system, but here, if you allow the active forces to change orientation, then again, minimum can change to another minimum and things like that. But here, we are making the athermal limit, so no thermal noise, as well as the active forces are held fixed. So only in that limit, one can have what we call a jam state. This is what I say here, that strictly speaking, if you use this definition, then that's possible only in the limit where the active forces don't change their orientation. And other thing is that, people are trying to understand the, yeah.
Now, even if they do change orientation, if the configuration is stable for all the forces that have been explored,
Mm-hmm.
still be
Yeah, but that remains to be seen. And if you randomly reorient these forces by some amount, whether the minimum that you had or the jammed configuration that you had will remain jammed, or there will be some changes somewhere in the system. Yes? So now you see here we have this state here, and we have this state here. This is sort of like a liquid, and this is sort of like a jam state. So, I mean, one would like to understand the property of this nearly jam state and the property of this flowing state. And this is happening for large values of tau p. So there is some reason to believe that if we understand the tau p going to infinity limit, the properties of the jam state and the liquid state in that limit, then may have something to say about the properties of those system in these intervals, where it remains jammed or remains a liquid. Okay, so yeah. So now I'm going to tell you about the results for the liquid state. Given the time situation, I will not be able to probably go into the properties of the jam state. So this is the liquid state. This is just a movie of the liquid state where I have two the particles are labeled by their kinetic energy and the particles are moving around, etc., etc. It's periodic boundary conditions. So now we'll begin to look at the properties of this liquid. So F equals 3 is here. F equals 3 is here, and it's very F equals 3 is here, top there, yeah, not this 3, that 3. And it is far away from the jamming point, so it's supposed to be a liquid. And it is a liquid, it continues to move. I mean, if you keep the value of F at 3, and then one can seems to reach a steady state, and one can look at the properties of this liquid. The first thing that one asks is the structure of the liquid changes. Now we have this active force on each of the particles. It doesn't change very much. As you can see, this is given in terms of this radial distribution function. And we get typical functions that look like liquid state radial distribution function, and one can compare them with that of the passive system and doesn't see a very big difference. And also, other thing that we have to look at is the system size dependence. And here, system size dependence is there, but it's very small. Now, this begins to change as you look at dynamical properties. Here, we are just looking at the structure. If we look at the dynamics, one thing that Schumann noticed at the very towards the initial stages is that if I now look at the kinetic energy per particle and look at its distribution in the system, it's of course not Maxwellian distribution. It's a non-equilibrium steady state. But that's not surprise. But the surprise is that it keeps on changing as you change the number of particles that you have in the system. And the shape of the distribution doesn't change very much, but the peak changes. The peak position or the average kinetic energy, which is peak position and the average are not exactly the same because of this tail in the distribution. They increase with m, and then eventually, I suppose, it will reach some constant value at large n. But we actually don't understand this this independence. And this is one of the things that we'd like to eventually understand. Why does the average kinetic energy changes as you increase the number of particles, keeping everything else constant? One reason where, one situation where one is sort of used to seeing strong system size dependence is something that you all know, near a critical point. And near the critical point, the systems exhibit strong system size dependence because there is another length scale in the system which is becoming very long. So what we try to sort of understand whether there is some kind of length scale in the problem which is becoming very long and which is leading to this kind of pronounced system size dependence. So to do that, I mean, for the positions, we didn't find anything interesting. Just looks like ordinary liquid. Looked at the velocities. And I'll just quickly go through this couple of plots. We are looking at now the autocorrelation function of the velocity, velocity of a single particle at time 0 and time t, how they are correlated with each other as a function of t. And the important thing is that it's not going to 0 at long times. It is going to a constant value, saying that each particle in this situation acquires a non-zero average velocity. And that makes the mean square displacement ballistic at long times. As long as the average velocity is non-zero, you will get a t-square dependence. So that's fine. But again, there is strong system size dependence. I'm sorry? Not always, no. The average velocity is oriented in the direction of the active force, instantaneous one start. So this is basically what is shown here. This is the angle associated with the force, one of them, and the other one is the angle associated with the average velocity, and they just follow the diagonal, saying that on the average, each particle acquires a non-zero velocity, which is in the direction of the constant active force that acts on that particle. So, I mean, this is already something which is sort of very different from what you have in ordinary liquids, where, of course, the average velocity goes to 0. But here, each particle has a preferred direction in which it has an average velocity. Total of them will go to 0 because that's how you choose the active forces, that the net force acting on all the particles is equal to 0.
Is that again the limit of high persistence that you're
This
speaking?
is infinite persistence.
Infinite persistence.
Yeah. So only then it is possible to do this kind of things because the direction of the active force is fixed in time. Otherwise, that will keep on diffusing, and then instantaneously one can look at the relation between the instantaneous velocity and the
size, do you have also a size dependence for non-infinite persistence? If you will be a little bit
not in great detail, but there is system size dependence. In the phase diagram that I showed, that the lines that you draw there, that will change as you change. So this is something that, again, is an observation that it's not so difficult to understand. I mean, it's just like, raindrop falling in the atmosphere or something like that. There's an external force, so and it's in a viscous medium, which is all the other particles, and then it acquires some kind of a terminal velocity. What is surprising is this, that now we are looking at, that was time correlation function. Now we are looking at the spatial correlation function at the same time. And here we are plotting 3 different kinds of correlation function. One is basically the velocity correlation function. One is the velocity and the active force correlation function. I'm sorry, this is just the FF correlation function. This is the FV correlation function. All of them look similar, and they go to 0 slowly. And where they go to 0, that depends on the size of the system. So there is a large correlation length associated with the velocities of these active particles, that if I look at the velocity at some point and velocity of some particle somewhere else, they tend to be correlated, and this correlation decreases as you increase the separation. But there is a length scale associated with that, and that length scale is increasing as you go to bigger and bigger systems. And so this is the 2 things that pictures that we should keep in mind. One is this VV correlation function, other is the FF correlation function. So this one I find even more surprising, because initially when we assign the active forces, they are done entirely at random. And then the system evolves with those assignment of the active forces through its own dynamics. And through this process, particles which have assignments of active force which are pointing in more or less the same direction they will come together in space. And, and then they move together. So there's this swirling motion or something like that that people talk about, that there are groups of particles which will sort of tend to move together. And the active forces on all of these particles, they will also be more or less in the same direction. 10 minutes, okay. And so, one can get length scales out of this decays. And if we plot the length scale as a function of system size, we'll see that the system's length scale grows proportional to the linear size of the system. This exponent is like half, and you have 2 dimensions. So square root of n is basically the size of the box. And the length scale that we get from those VV correlation function continues to grow linearly with the size of the box. And this is very similar to something that you are to expect when this length scale actually diverges in the thermodynamic limit. So from this, of course, limited size correlation, limited size of the boxes that we have looked at. But from this, the tentative conclusion is that liquidity is critical in the sense that the correlation length diverges in the thermodynamic limit. And this other thing is what I talked about. The self-organization I find very interesting in the sense that here we have a very simple system of particles interacting with some simple interaction. And you say that there are forces acting on all those particles. And these forces don't change as a function of time. And these particles, through their dynamics, will eventually rearrange itself into a liquid state in which the particles which had forces more or less in the same direction, they will be spatially close to each other. One can see why that state may have a long lifetime, because if you have a bunch of particles which are close to each other, which are moving in the same direction, then not many collisions, and so that state might have a long lifetime. But how the system actually comes to that state through the initial assignment, which is random, is something that I find interesting, and we'll be looking at that in the near future. Okay, so this is the property of the liquid, I think. Oh, this is some picture where you see this swirling bunches of particles. That this color scheme is, the light is where the particles have high velocity, and if we actually look at the directions of the velocities, then we'll see that they're more or less parallel and they're moving parallel, but the overall direction is changing. And the net velocity of the center of mass velocity is equal to 0. So if they cannot be all in the same direction. So you cannot see flocking, but you can see swirling. So the remaining 5 minutes, I will tell you a little bit about the dynamics of the jamming process. And this has a connection with some question that was asked about whether eventually the system will jam, go to a minimum and stay there or not. So what we do is start from the liquid that we just discussed, f equals 3, to a small value of f, and then run the simulation to see whether the system remains fluctuating or whether eventually it goes into some kind of a jam state and then stays there at later times. So this is just a picture, is a movie of this jamming process where this blue corresponds to 0 kinetic energy. The system is trying to go to a state where the kinetic energy is equal to 0. And it does so very intermittently. There are states where everything sort of looks like blue, and the question is, then if you continue to run it for a longer time, then there will be some nucleation of some plastic event, which will further reduce the energy. So this is in some sense, this is intermittency that I talked about, not in this context, but in a context where the f is constant. But here you are doing this quench, and the quench itself is intermittent. And time to reach a jam state increases as the value of f to which you quench becomes larger. So f equals 0 quenches quickly, reaches, and f equals 1 takes long time, and 1.65, which is close to the threshold as found in that earlier paper, it takes a very long time. So I'll be done in about 3-4 minutes. Okay. So this is the process of jamming, and again, there are some interesting issues there. So what you're looking at is the kinetic energy, average kinetic energy, as a function of time, when you are quenching the system from this initial liquid state to a value of f, which is small. And you can quench it to different values of f. These are the values of f that I'm writing down. And then we look at how the kinetic energy changes as one progresses in time. So for initially, when the final state has very small value of f, one sees some kind of a power law decay of the kinetic energy. And this has been seen earlier by Peter Solich, Chaco, and others for passive systems, where you take the system at very in a random configuration and then quench it to t equals 0, and one looks how the kinetic energy is changing. There they found this power loss. So this is fine. This is when the activity is small. But as you crank up the activity, this simple decay becomes very complicated. And you see that there is initial decay, then there is something that looks like a plateau, and then there is an eventual decay from the plateau. And the length of the plateau increases as one goes to larger and larger values of f. Now, if I have a picture like that, then it's difficult to conclude anything about a threshold, because if this one will eventually jam, whether this one will eventually jam at what time scale, that is something that we cannot tell, because the simulation cannot be done for arbitrarily long periods. Yes. I'm sorry? Yes. And these are, of course, not single runs. I mean, single run would be very, very jagged. But these are averaged over like 500 runs or something like that. So you get something which is smooth. So the plateau is so between here and there, as you can see, although, I mean, really don't have a plateau here. But as you go to bigger systems, so then we'll see that. There will be plateaus, and there will be time scale associated with eventually when it gets into this jam state. So this is what we looked at then, how this time depends on the value of f. And we find that this time increases rapidly initially, which can be fitted by a power law. This is sort of like the mode coupling theory of glass transition. But beyond a certain value of f, this power law diverging form doesn't seem to work anymore, and one finds something which is exponential, which of course says that it's not going to diverge at any finite value of f. So this picture would argue against having a threshold such that below this value and above this value are different. But again, there is strong system size dependence. So we also look at system size dependence. When you quench to f equals 0 and also quench to f equals 1, again, you see very strong system size dependence. And if you go to bigger systems, then it takes longer to reach this jam state. And the time, again, increases with the system size as power law, at least over the limited range that we are looking at. So here also, there is no sort of special value of f. Even for small value of f equals 0, f equals whatever it is, f1, one sees power laws. The only thing that changes is basically the power of this power law. And here also, there is no indication that there is a critical value such that something different happens when f is bigger or smaller than that critical value.
On the plateau, it is liquid.
Yeah.
It's like a metastable liquid state.
Right. It is something go to 0 here. Some quenches will go to 0 there in these figures. In this figure, there is not a single quench that will go to 0. But if you could run it for 100 times longer, then one needs to see. But that's why you need the extrapolation. And the extrapolation doesn't predict that this time actually becomes infinity for any value of f.
Yes, I don't understand. I don't understand this stuff. Because if you have a run that never stops, how you count the mean time?
Yeah, so where the points where we have calculated, everything goes to the jam state. Okay. So here you see this one that doesn't seem to stop, that is at 2. And in the next picture, we don't have anything that goes all the way to 2, because there we cannot estimate what the time is going to be. So this is probably, I don't have time. Just one line about, we have also looked at the jam state, and one of our sort of, again, tentative conclusions is that the jam state that we get depends very much on the jamming protocol, and also that some properties of this jam state are different. And the property that you have looked at is the distribution of contact forces. And in the passive system, this is supposed to exhibit some kind of a power law distribution at the jamming point. But we seem to find that for this situation, again, in the jam states, one can define these are states which are not changing as a function of time, and one can look at the contact force distribution. There is scaling, but the scaling function doesn't seem to have a power law form. So, but that conclusion remains to be confirmed by more calculations. So this is the scaling function which seems to have a gap. So yeah, so I more or less finished in time. So this is
Thank you very much.
these are things that I've already told you about: velocity correlations, self-organization, critical force, system size dependence, intermittency, and this I didn't have time to go into, but we need to do more work to make this more concrete. I would expect to be generic if we don't have some funny-looking potential. See here, Leonard-Jones, just want to point out this is also something that's important, because at this density, only the repulsive part of the Leonard-Jones potential is important. So if we had just other potential which is repulsive but falls off quickly as a function of distance, I would expect to have the same behavior.
Yes, I had a question. So all your simulation, you did them at like constant number density, right? And so if for the potential, you're taking a hard sphere potential, then I would expect that there is a single, like dimensionless number, like persistence length divided by size of the obstacle. But what you're showing us is more like a two-dimensional phase diagram in terms of the force and the persistence time. How are these two things compatible?
Well, I mean, first of all, I mean, I'm not sure that the hard sphere system will have the same phenomenology as what we have done here. Here also one can define that kind of a parameter. I mean, there is a persistence length and there is a size of the particles. So it's not just that parameter which is important. It depends separately on the values of the persistence time and the strength. Also, there is a strength of the potential. And hard sphere system, it may not depend only on the value of this non-dimensional parameter that we are talking about, but I cannot think of any other non-dimensional parameter in that particular sense. So we'll have to see.
Okay.
I'm not sure about that.
Okay, thank you.
So I was wondering, you mentioned that the jammed state is a local minimum of the Hamiltonian, right? So
Or the Hamiltonian in which we include
the forces, yeah. So the fact that there is a jamming transition, does that mean that above a certain threshold force there are no such local minima
that is
anymore?
that is the question. That
Or-
whether this minima disappear or the time the system takes to reach such a minimum
Right,
also diverges in the thermodynamic limit in a way which is different depending on
right.
whether force is above or below a particular threshold.
But that is not known, or is
That
it?
is not known.
Okay, thank you.
So when you showed these quench plots like for different times, so when it reaches the plateau, for example, at larger persistent time, so is it an interesting parameter to look at the orientation of velocity correlation during that quench? Like for example, when you have a almost constant average kinetic energy for long time, so some orientationally is it?
Yeah, so I mean the kind of correlations that one sees in the liquid state, which is a stationary state, whether those
Yeah.
things are also seen in the plateau.
Right.
I cannot tell. I would expect that it's not going to be very different because the value of f is fixed. I mean, when you do the quench, the final value of f is fixed.
Mhm.
So the system basically tries to quote unquote equilibrate at that value of f in the liquid state, and eventually there is an absorbing state to which at still longer times it gets convergence to that.
Okay, thanks.
Like if we change the boundary conditions to in a box, and do you think things might change? Because if it's periodic, then it's a non-gradient force, right?
Yeah.
So it could be in a non.
So yeah, those Hamiltonian that I wrote down will not work when you impose periodic boundary
So
conditions.
if you change box, probably it will be different. Is that
It would be different. If you have boxes, then it is known that active particles have sort of strange behavior near the boundaries. I mean, this tend to aggregate and things like that. So
you won't have this transition and
I think the phenomenology will be quite different in that case.
So I have one question.
Yeah.
So there is very nice the fact that you have this size dependent and the correlation that diverge. So I was wondering, because in the system I studies like this, if you decrease f from 3, let's say, to 2, it will be nice to have to see if this velocity has a bigger
Yes.
correlation.
Yes, and this is also related to the question of whether there is a threshold value. As one comes close to it, if there is a threshold, then as you come near the threshold, then one expects some kind of divergence and things like that. Yes. But yeah, it remains to be seen.
Okay. So now we have Srikant is there. So thanks again.
clip, is it?
So Sri, I will do 10 minutes before 45. I will tell you.
Yeah. 10 minutes before I have to stop, whichever way you count. Yeah. So do you have the, okay. Okay. So it's a great pleasure to join in this part of the celebration of RRI's 75th anniversary, and my best wishes to colleagues here and the institution that it continues to have the stimulating and exciting ambience and scientific culture going forward as it has had for most of the 75 years before. And I thank Sanjeev for this invitation to speak at this meeting and to interact with all of you. What I'm going to talk about today has some of the same keywords as Chandan's talk, but otherwise is going to be rather different. So I'm going to tell you about some investigation that we've made, looking at the spatial dimensionality dependence of the glass and jamming transitions. This is work that was a part of the PhD thesis of Manoj Adhikari, who graduated sometime last year, and this work was done in collaboration with Smarjit Karmakar at TIFA Hyderabad, and the work has appeared recently in this article after a rather interesting journey. Okay, so anyway, so here's the outline of my talk. So I'm going to say very little about the glass transition and the jamming transitions. This has been, to the extent that it was needed, it has already been introduced. And I'll spend some time on talking about the relationship between these transitions as people have discussed in the past. And I'll then mention the phase diagram that one gets from mean field theory in infinite dimensions of the hard-sphere glass transition. Okay, and this is going to be a reference point. So the overall sort of goal of the work that I'm going to present is to sort of look at a scaling analysis of the dynamics of hard sphere fluid or soft sphere fluids, actually, in order to estimate from that the ideal glass transition density of the corresponding hard sphere system. Okay, I'll explain what that means. And so I'll start by telling you about some work that was done in this direction in the past for 3 dimensions. I'll then tell you about our analysis of the same question, but this time looking at dimensions from 3 to 8, okay? And I'll then tell you how our results compare with some recent attempts to extend the infinite dimensional theory to finite dimensions, and I'll then summarize. Okay, so so the glass and the jamming transitions are 2 routes through which you can go from a fluid state to an amorphous solid state. And typically, when one talks about the glass transition, one has atomic and molecular systems in mind, silica as a concrete example, and whereas the jamming transition is typically something that one discusses in the context of granular matter. So these are 2 sort of extreme examples where jamming and the glass transition are respectively relevant as the transitions to an arrested state. But there are plenty of examples, such as colloidal suspensions, where in principle the sort of the phase behavior as well as the rheology of the material can depend on both phenomena, and this is fairly well appreciated. To say a little bit more, the glass transition is reached typically upon cooling a dense liquid, and it is characterized by a divergence of relaxation times as the glass transition is approached, and below the divergence temperature, of course, you have a system where particles are not, since there was a question about this, are caged permanently and do not have any translational motion or displacement in the long time. And the glass properties that one has depend on the protocol of preparation, such as the cooling rate. And this is something that's illustrated here, where if I take a supercooled liquid and I cool it down, what I end up with depends on how fast or slowly I cool. And the limit of infinitely slow cooling is something that's of interest, which is called the ideal glass transition, and the corresponding temperature is called the Kaufman temperature. And in our case, it's going to be a density that we're going to be interested in. So 2 points here. There is an understanding, which nobody is very surprised with, that the glass transition temperature and the properties of the glasses depend on the protocol with which you prepare, but you have an idea of a limiting temperature or a density, which is a unique point. Okay. Now the jamming transition, again at the same level of giving you a brief summary, is observed when you have assemblies of mesoscale or macroscale grains or particles, and the control parameter here is the density. The temperature is not important, and the rigidity of the jam packings is determined by mechanical contacts. So they're pinned rather than caged. Yeah, so they don't have any kind of thermal-like motion in the jammed state, and correspondingly, if one is looking at rigid particles, there's a divergence of pressure at the jamming transition. Okay. Now the hard sphere system has been employed to investigate both of these transitions as an idealized model system, and for sphere packings, conventionally, one says that sphere packings jam at a packing fraction of about 64%, and this is called random close packing. And there's sort of a long history of people thinking that this is somehow a very unique and well-defined density, and people have pondered the question of where this number comes from. Okay, but if one looks at the not granular piles, but like the hard sphere system, and asks questions about the phase diagram, one can sort of begin to sort of question that idea that there is this unique density, and it's very much through a thinking along the lines of the cooling rate dependence of the glass transition. Okay, so the basic idea is as follows. If you look at this graph here, which is from a numerical investigation by Robin Speedy, where he looked at a hard sphere fluid, which he then, I won't go into the details, so what is plotted here is the inverse of the pressure. So the liquid branch comes like this, the equilibrium fluid branch, and basically if along this equilibrium fluid branch, if you were to sort of fall out of equilibrium at different densities, and then upon further compression you follow a different equation of state, the glass equation of state, then you end up at different points along the x-axis where the quantity plotted on the y-axis, which is the inverse pressure, goes to 0, and that would correspond to the jamming point. Okay? Now, so here, this picture is very much like the picture of a glass undergoing the glass transition at different temperatures, depending on how fast you cooled it. So you can imagine that the reason you enter, you sort of deviate from the fluid branch and go into the glass branch is because you fell out of equilibrium. Okay? So,
What controls the fact that is the preparation?
yeah, so you could say that it's preparation, but there are different ways of talking about it. So for example, Torquato and colleagues, who also sort of draw now the equation of state turned upside down, pressure instead of inverse pressure, they sort of pointed out that there is a possible range, there's a range of possible jamming densities, but they attributed it to some kind of ambiguity in what you mean by random. Okay, and so they said the packings that you prepare which are jammed can have different degrees of order, including crystalline order, and this could be the reason why you have a range of jamming densities. Okay, whereas somebody like Speedy would.
This is the initial condition.
No, so hold on. I'm actually going to say something specific about it, but you could sort of imagine, just like you cool a liquid to undergo the glass transition, you have a procedure whereby you compress the hard sphere fluid, and in fact there is something called the Lubachevsky-Stillinger procedure where you do it at certain rates, right? Just like a cooling rate, you have a crunching rate, and this crunching rate determines when exactly you fall out of equilibrium, just like the glass transition. Okay, so this is one way of thinking about a protocol dependence of the jamming density, but the other way is to say, I might end up crystallizing part of my sample, and therefore what you have is not really a random close-packed structure, but something that has regions of crystalline order or some other higher order, right? So that's what these colleagues sort of argued. So,
Just one
yeah.
further question along these lines. When you talk about fast or slow cooling rates,
Right.
the system has to have an intrinsic relaxation time
Yes.
for that to be meaningful, right? But if you're just looking at hard sphere configurations,
Yes.
and you're talking about crunching rate,
Right.
what time scale are you comparing it with if these things aren't doing Brownian motion or anything else?
Well, so, I mean, if you were to do this, you do it at a given, kinetic energy of the hard sphere system,
So you actually give
which
the
would
particles a
then determine a time scale.
You do the particles a kinetic
Yeah. No, so, I mean, that's what's done in the Lubachevsky-Stillinger procedure. You might do other things, right? Okay, so then, so some years ago, some of us, Pinaki Chowdhury, Bharti, and myself, we decided, let's sort of get clarity on this issue of what protocol means, right? So we did something very simple-minded, which is we simulated the hard sphere fluid at various densities where we could reasonably be sure that this was the hard sphere fluid, right? So no crystallization. And then we said we subject these quote unquote equilibrated fluid configurations to the same protocol of jamming, right? I won't go into the details of how we did it, but the idea is what differs from case to case is the density at which the hard sphere fluid is considered in equilibrium, and then you apply the same protocol. And what we found is as a function of the fluid density, which is on the x-axis, the jamming density, in fact, is variable. So at very low initial fluid densities, what you end up with is jammed configurations which have this random close packing value. These are binary systems, so it's not exactly 64%, it's a little bit higher, but that's a detail. But as I equilibrate my fluid at higher and higher densities, I begin to have a jamming density that's higher and higher. Okay, so this sort of clarifies the point that the random close packing, which variously is called the J point, is a limit value of a range of densities over which jamming can occur. And of course, I need to sort of present more of an argument to say it's the lowest jamming density, but for the purposes of this talk, let's go with that. Okay, so that seems simple enough, but not everybody over the years has agreed with this viewpoint. And basically, there are two studies here of people who, who've thought a lot about this problem, and based on some form of a free volume equation, theory of the hard sphere system, they both argued, in the case of Kemian and Liu, they sort of argued that the high density equation of state of hard spheres is in fact well described by a free volume equation of state with a jamming density around 64%. Therefore, they said this is a well-defined value. Cornelio and company again did a cell theory where they concluded that there is indeed a jamming line, but as you go to higher and higher values of this jamming line, the corresponding glass transition density also converges to the same value. So that if you think of the Kauzmann density as the highest density along the fluid branch where you can have the glass transition, that Kauzmann density converges with the corresponding jamming density. Okay, so this is a very different phase diagram. So this question, therefore, based on these works, don't present the same conclusions as what I suggested earlier. Okay. Now, in this context, if you look at the infinite dimensional theory of many people, Parisi, Zamponi, and co-workers, the phase diagram is something that's sort of sketched here, where I won't worry about marginal glasses. They're not sort of pertinent to this talk. But basically, once again, if I look at the inverse pressure, the fluid equation of state, there are different points at which I can deviate from that fluid equation of state into a glass equation of state, which will terminate in the jamming point. So there is indeed a range of densities over which jamming can occur. Okay, there's a range of densities over which the glass transition can occur, and a corresponding range of densities over which jamming can occur. And these ranges don't have any, a priori relationship between the two, because for each glass transition density, the jamming density I should expect to be higher, but if I look at the entire range, it'll be shifted, but there's no particular relationship between the two. Okay, so there is some supporting evidence for this kind of a picture from three-dimensional simulations, but the particular simulations that I'm mentioning here do not make any attempt to precisely identify where the jamming and the Kaufman densities are. Okay. By the way, from now on, when I say jamming density, I mean the lowest jamming density, or the J point, as some people have called it. Okay. So there is a range. Okay. So here is some more simulation data, which shows basically the equation of state for a hard sphere mixture, and these points are basically the pressure. And what this diagram illustrates is that you have finite pressures even beyond the RCP value of the jamming density. Okay, so you have an equilibrated fluid at higher densities than the jamming density. Okay, okay, but once again, an attempt was not made to identify exactly where the Kaufman density is and the jamming densities are. Okay, so but this question of where the Kaufman density might be for the hard sphere fluid in 3 dimensions was made, sorry, let me say that again. So this work of Berthier and Witten addressed the question of where the Kaufman density is for the hard sphere fluid, but they did it through looking at data, simulation data of dynamics coming from a soft sphere system. Okay, so the basic idea is, I'll say more about this soon, but the basic idea is that if I were to sort of think of a soft sphere system at different densities, and I imagine that there is a density at which there's a divergence of relaxation times for the hard sphere system, below that density, the soft sphere system will show one type of behavior, and above the density, it'll show a different, stronger temperature dependence, okay, because particles have begun to overlap, right? So if you look at the raw data, this is what you see. This is inverse temperature, and this is relaxation times with the square root of T scaling. And you see that at low densities, you have sub-Arrhenius behavior, and at high densities, you have super-Arrhenius behavior. And these, you can actually do a scaling analysis to collapse onto 2 branches, one sub-Arrhenius, one super-Arrhenius, as follows. So the 2 considerations that go into doing that analysis is first to say the soft spheres at finite temperature I can treat as hard particles with an effective diameter. And these guys took the effective diameter as the one given by the number density minus a temperature dependent factor. And the second, whether, so we'll come back to this question of whether this is the best way to do an effective diameter calculation, and it's not. We did something a little bit better, but that's also not the best way to do it. But that's one idea. And the other is to say that if I look at the hard sphere system, the relaxation times diverge in an activated form as given here, which is exponential of the inverse of phi minus phi naught raised to some power delta. And there is evidence from work in 3 dimensions, including experimental work in colloidal systems, that suggests that this exponent delta has to be 2. Okay? And so if we take these 2 things in mind, I start with this equation, and I replace the packing fraction phi here with an effective packing fraction, right? And do a little bit of manipulation. I can then end up motivating a scaling form for the relaxation times as follows, where this function f plus minus correspond to the functional form below the density phi naught and above, which has a scaling variable that's given here. Now, okay, so one can sort of argue that these functions should asymptotically go in a certain fashion as a power of the independent variable, and in order to have right at phi naught Arrhenius behavior as a function of temperature, you need these exponents mu and delta to satisfy this relationship. Okay, so this is what Berthier and Witten did in 3D, and so they sort of managed to get rather impressive data collapse of their dynamical results, but and this gives a value of phi naught, which is what we are estimating to be the Kaufman density, right, which is about 0.635, and the other exponents, delta and mu, sort of come out reasonable but not exactly okay. Delta was expected to be 2, but the soft particles. Right. No, you're simulating soft particles, but you're using it to get the corresponding hard particle Kaufman density. Okay? So, because this relation is supposed to be the relation that applies to hard particles. Right?
But then what it means the temperature for a
What it means is that the effective diameter of the hard particles you're thinking about is determined by the temperature at which you simulate the soft particles. So when I have soft particles at a given temperature, there's an effective diameter, which is an effective hard sphere diameter. Yeah? Okay? Okay, so anyway, now, so the result of that analysis is that you get a value of this Kaufman density, which is actually rather close to the jamming density, and therefore it doesn't really permit you to say something about how these are related, right? But there was something that was a little worse, which is some colleagues, Maiti and Schmiedeberg, pointed out that they could get sort of comparable data collapse with simulation data of soft spheres with rather different values of the parameters involved. So one of the questions that we wanted to address was how to sort of do a more systematic job of estimating this Kaufman density. But there are more questions. So one is, as I said, how to do the estimates of phi naught and phi j reliably, but how do they depend on spatial dimensionality, okay? Can these densities be determined by a more robust procedure? Do the results more convincingly distinguish phi naught and phi j? This is sort of related to the question of the Cornelio et al. Analysis. Can we compare our results satisfactorily with attempts to extend the infinite dimensional results to finite dimensions? Okay, this is sort of the questions that we have in mind. What we do is simulate a harmonic soft sphere mixture, 50-50, with a size ratio of 1.4, and we do this in dimensions from 3 to 8. Okay, I won't say more. This is all the relaxation times that we get as a function of the density and temperature for each dimension. Okay, and we take these results and we do our scaling analysis, which is based on basically taking a fairly simple-minded effective diameter theory for from liquid state theory, the Barker and Henderson expression, which says that the effective diameter is given by this integral here, where u is the interaction potential between two particles. And if you plug in the soft sphere interaction potential you have, you can get an expression for this effective effective diameter, which is different from what Berthier and Witten used. And this, of course, actually is an approximation, but we from here, in different dimensions, you can write down an expression for the effective packing fraction, which can get longer and longer as the dimensionality goes to larger values. But we sort of make a choice to say we'll keep the exact first order square root of t term, and the rest of it we approximate by a t to some power beta. Okay, and these then the coefficients, actually the first coefficient is exactly given. So the second coefficient and the beta and the these are going to be our sort of fit parameters in doing the scaling analysis. And this is so doing exactly what was done before. If we take this expression for the effective diameter, plug it into the hard sphere expression for the relaxation times, and do the same manipulations as before, we get now a similar looking expression where the scaling variable is different. And with this scaling variable, to obtain Arrhenius behavior at phi equal to phi naught, we require delta equal to 2, which is interesting. Thank you for asking. No good reason at all. Except if you're thinking of phi naught coming from higher densities as the density at which the glass transition temperature goes to 0, and if you have in mind a VFT form for the temperature dependence, then you go to Arrhenius. Otherwise, no good reason. Okay, so now what we've done by sort of going through this procedure is we now have more parameters. We had the delta and the phi naught, but we have this B and beta. And so what we said is we're not going to use dynamics to estimate all of these parameters. We're going to use the equation of state, which in principle we can also say should be described by a single effective density, right? So the equation of state in terms of an effective packing fraction here, we sort of, these are the raw data at different temperatures, and we say this should collapse into a single equation of a hard sphere-like equation of state, and we use that to estimate the B and the beta, which only appear in the expression for the effective packing fraction with this kind of data collapse. And then we use the dynamical data only to extract phi naught and delta. And even as I'll mention, based on, in fact, the results that we get, we conclude that delta equal to 2 is a good choice across all dimensions. No explanation why it should be so. But that's what our data tell us. So we ultimately fix delta also to 2 so that we're only estimating phi naught from looking at the dynamics. I'll skip this. So this is basically all the scaling collapses that we get. This is, okay, just to say that we can go back and do the analysis that Berthier and Witten did, and we actually get reasonably comparable phi naught values. So even though I said something about a better way of doing the analysis of the effective diameter, it doesn't make that much difference at the end of the day, but it's a good check. Okay, so we also worried a lot about sort of the error analysis involved in the scaling collapse, and there is something to worry about. So if I look at sort of the error that I might define in some way in the phi naught delta plane, you actually have sort of these correlated values over which the error, and I, you know, at the end of the day, this is as good as it's going to be as good as your numerical data, so we don't have much to say about it, but it does indicate that delta equal to 2 is a good choice. Okay, so with all this, what do we find here is the phi naught values that we estimate, which as I increase the dimensionality, goes to lower and lower values. And then we use, yeah, perfect. So then we use a procedure that had been followed earlier, where we start with initial configurations. In this case, we deliberately choose very random configurations because we want to estimate the lowest jamming density. And we subject it to rapid compression and till our energies reach a certain value, and then we do a decompression till they reach negligible values in order to determine the jamming density. And this is a finite system, so there's a distribution of these jamming densities, and we use the average values that we get from such a procedure. This is how the distributions look, nothing spectacular from all the dimensions. Okay, so with that, we can now plot as a function of the spatial dimension the phi naught values and the phi j values. And they don't look very spectacularly different from each other. They're actually very close in all spatial dimensions. But if you look at the ratio of the two, you do see that indeed there is a meaningful change. In 3 dimensions, the phi naught value is actually a little lower than the phi j value, the jamming density. So the glass transition density is a little lower than the jamming density, but as you increase the spatial dimensionality, it goes up by single-digit percentage values, but there is a systematic change in the relationship between the glass transition and the jamming densities. Okay, so as I said, one of the sort of goals of this analysis was also to see if we could say something about what estimates of the glass transition and jamming densities people were able to make in finite dimensions. So the people in this particular case are Mangyat, I hope I say it right, and Zamponi, who basically did, an approximation scheme around the infinite dimensional solution to obtain the glass transition and the jamming densities. So I have to explain this a little bit. When one talks about the glass transition, as I mentioned, there is a range of densities over which one can imagine the glass transition taking place. And the smallest of this value in this literature goes by the name of phi d, which is the dynamical transition density. And then phi k is the highest density at which the glass transition can take place. And similarly, for the jamming, there is what's called a threshold density, which is the lowest density at which jamming can take place. And there is a highest density at which jamming can take place. And so these have been estimated. So the higher values actually scale as a dimensionality, whereas the properly normalized density values, whereas the dynamical and the threshold densities saturate. Okay. Now, how well do they do? One thing I should have said, I think it's on the slide, is that by the authors of this work, I don't understand the details, but estimating this threshold density is actually very hard, and people like Zamponi say that what they have are actually pretty poor underestimates. Okay, and this indeed shows up when we make a comparison. So the AKS is our results. So AKS circles are our glass transition densities, and MZ is how do you say the name? Mangia, okay, and Zamponi. So that's now this is the jamming density, and you see that indeed this is a very poor comparison, even though the trend is right. But if you look at the glass transition densities, our results are the cyan circles, and the results in squares are the analytical results. And on the one hand, we can't really say whether it's going as log D, which is what the theoretical prediction is. But surprisingly, quantitatively, these numbers are quite close, which says that that approximate theory is actually not doing badly. Okay. Okay. And this is just another. This is the last slide, actually. This is now showing all the temperatures and densities that we simulated, and at each density, the Vogel-Fulcher-Thaman divergence temperature, And one thing you can do is to ask if for a particular dimension of the system, if I vary the density, what density is it approaching? And in 3 dimensions, actually, it's kind of difficult to tell because the jamming and the glass transition densities are sitting at the same place. But as you go to higher densities, it's clear that your VFT temperature is actually approaching the glass transition density rather than the jamming density, which is an obvious point that we can now say with more confidence. Okay, that's a summary. I won't read it out. Thank you for your attention.
Thank you very much.
You talked about the reaching to different jam state from different initial density,
Right.
and different initial protocol also you can get the jam state. Now, if you have 2 jam state and coming from 2 different density or different protocol, is there any property of these 2 jam state which can different these 2 jam state? Or all the jam state, whatever the protocol, whatever the density you come, all are same properties wise.
So there's some properties that do not change. So one of the things that I didn't talk about because that's really an old piece of work is that you can ask whether, if these are soft spheres now. So above the jamming density, how does the pressure scale, how does the mean contact number scale, etc., with the excess density is something that you can ask. And actually you find that they don't depend on the density at which you jam, okay? But on the other hand, if you look at sort of an experiment like shearing, right, and you ask what is the steady state or flow stress that you reach, these are actually very different, okay? In other words, yeah, so I can explain to you. So there are some not so obvious properties where they differ, but in terms of like the critical properties near the jamming point, they don't change. They don't change. Yeah.
Hardly worth a mic, sorry, but kind of a dumb question. I was just wondering, when you go to these very, very high dimensions, the number of particles on a side is very small. Does that small linear extent not matter? Is really what counts the total number of particles implicated rather than, is that why it's okay to have 3 particles on a side and 8 dimensions for 5,000 particles? I mean...
Oh, you mean in terms of system sizes?
Yeah, the effective linear size of the system is very small.
So
is that somehow unimportant, is what I'm wondering.
So basically, you're reaching sort of the mean field. I mean, yeah, even if you look at one coordination shell.
Because you've got enough neighbors,
Yeah,
it doesn't
so,
matter that in a given
right.
direction it's small.
But I didn't mention that point here. We sort of do have to worry about making sure that our interaction range fits into the box even when we go to high dimensions, right? So yeah, that we do. But yeah, I mean, this is what is said, so I'm repeating it. How big a system you look at matters less and less as you go to higher dimensions.
Okay. Other questions? So I have one first about the one work with you and Berthier where you show this dependence of the jamming transition. So if I understand well, what you are saying is if I take a configuration of art spheres, which are equally likely at some density and then I crunch, I found some jamming, and then if I do a higher density, it will be more difficult, but then I will find a bigger value of the threshold. Is this one?
Right.
Okay.
That's right. That's the, yeah.
Okay, and so did you find some, I imagine that, did you find some finite size, or not finite size, I mean,
what is
some
that asymptotic value?
So yes, I would like to understand if this value is finite, if you do it.
Well, so, okay, so one could sort of actually extrapolate. So if you have, so this is the phi initial, and this is the phi jamming. So you have like some behavior like this, right? Where initially this is much higher, but at some point, these two lines should cross,
Exactly.
right? So it won't look like this. I think it'll look like,
Yeah,
it'll probably look like that. And so you could, yeah, but I don't know. We haven't done that exercise, but that could be an interesting thing. Yeah. Yeah, Rajesh has a question.
Yes.
Right. You mean this one? Yeah. So we did have error bars, and these are outside the error bars. But yeah, no, I mean it's second decimal place accuracy is not so hard. So yeah. No, so like I showed in the later work, we do look at distributions like this to get an idea, how distinguishable. So they are, yeah. So I can share with you. They are distinguishable. But
So maybe my last question is about this criterion by Berthier, Witten. So, but why this? I mean, you are if I understood well, you take soft sphere and you say if the relaxation is subarrhenius, I'm in the fluid phase. Otherwise, I'm in the glass phase.
right,
If it's superarrhenius,
right.
this is the criterion.
Subarrhenius, superarrhenius. Yeah.
And everybody agrees, or?
What's there to disagree? I mean, no, so the point is simple, right? If I look at, if I'm sitting below some threshold value of the density, as I go to zero temperature, right, I ask what will happen to the dynamics, right? It'll go to a hard sphere limit. Right, because I am going to end up in the limit of zero temperature in the hard sphere fluid, right? Whereas if I'm sitting above this Gaussman density, right, then hard spheres can't exist there, right? So necessarily your soft spheres have to overlap, and so what I have is a dense compressed liquid, which I expect will have a finite glass transition temperature. So the functional form of the relaxation time is different.
Okay. Okay.
Okay. Maybe I'm not doing a very good job of explaining.
Okay. So thank you very much. So thank you, Sastry.
Thanks
Thank you,
very
Chandan.
much.
So now is the time of the lunch.
Can I just say something? Yeah.
Yes.
No, I just wanted to mention, I forgot earlier, two things. One is, so there are posters by my students on something that not directly related, so I would like you to take a look, by Swarnendu Maiti and Debarga. And also for the students, if any of you are interested in sort of joining forces with or the senior colleagues, for that matter, you're most